All right, peeps, here we go. 2.1, Chapter 2, Ecology. 2.1, Individuals, Population, Communities, and Ecosystems. Do me a favor, define the following terms. Page 106, species, population, community, habitat. Species, you should be able to get pretty good for all those, actually relatively pretty quickly. So, hey, just if you do hear me scream, it's just because there's a mouse that I saw in my basement here. And I'm all for biodiversity, but not in my house. So if you do hear me scream, that is why. Uh, what's what in ecology? So taxonomy. It's the naming, describing, and classifying of organisms into a hierarchy. You might remember this from biology from last year. It's how we name things. Each species is given a two-part name, a genus, then a species name. So the genus comes first, and then the species name comes second. Population density equals average number of individuals per area. So if our school is 33 acres and there's 700 students and we'll say 100 other people, just make it even math, it's 800 people divided by 33 acres. So, yep, that's your population density. Things that affect population density are natality, birth rate, how many people are being born. Also mortality, death rate, how many people are leaving. All right. Migration would be another one. You could have immigration and also emigration where people are leaving. So same thing for species. Hey, look, if there's wolves in an area, a lot of animals are going to be emigrating. They're going to be leaving one way or another. Yep. So define the following terms. Page 107. Ecosystem, niche, biotic factor. Oh, looks like, sorry, peeps, looks like you only have to do that once. My fault. Ecological niche. All right. Organisms need a particular set of conditions, a niche, in order to really live and thrive. Biotic factors are their living conditions, and abiotic factors are the non-living conditions. Nature won't allow two species to inhabit the same ecological niche at the same time and place. So there are some ways to look at it. Two niches of example. Kirtland warbler. It only breeds in the forest with young plus large jack pine trees with sandy soil. I believe this is in Scotland. The trees are 2 to 4 meters tall, and which is around, and they're about 6 to 20 years old. So 2 to 4 meters tall, that is roughly 7 feet to 7 to 14 feet. Low ground cover and no tree canopy helps them on out. So that's what they're looking for. Forest, once they start to grow old, the branches break off and then the birds leave because they've got really no protection, no place to nest. And they winter in the Bahamas. So, yep. Common prickly pear cactus would be another example. It likes dry desert, hot days, cold nights. There's no moisture really to trap in the heat in the desert, so that's how you have hot days and cold nights. Needs dry, sandy, or gravelly soil, so if it does rain, it just goes away really fast, the water that is. Stores water in fleshy pads, that is the cactus itself, and waxy leaf to reduce water loss. If you've ever realized fruit at the supermarket, like apples, they'll have this like sheen to them. They didn't fall off the tree just shining. What they do is they put this wax around them. It's usually like a honey wax that they get from a beehive, something like that. But the wax basically keeps the moisture in, and it also keeps air from getting in to oxidize it. So it keeps the apple fresher. This cactus has the same sort of thing with the waxy leaves to reduce the water loss. The spines to prick herbivores too, because if you're a cow out there just going and looking for something green, but there's nothing green around, but then you see a cactus, you're like, oh yeah, yummy. I'm getting in on that. And then like you go to bite it, obviously you got a tongue full of prickers, and then you realize not to eat that. Shallow roots for the cactus as well. Why? Because when that water hits, it can suck it up really fast, but it doesn't get drowned in it either. Antifreeze chemicals in its cells. So it's got these this chemical in the cell structure that basically during the cold night, it keeps it from really dying, basically. So, yep. All right. Let's go on with population interactions. Organisms, like everything, don't stay the same. They grow, they eat, they age, they die. Think about yourself. What do you like for food now? Is it the same when you were 4 years old and the only thing you were eating was brownies, cheese pizza, and cheeseburgers? Right? Things change. So, and mostly that's for the good. So, things that change ecosystems. Humans do. Yep, quite a bit. We're probably the biggest change that an ecosystem can have. Fire does, natural fire or caused by humans. Natural disasters, hurricanes. We talked a little bit last time about that hurricane that just hit North Carolina. And animals. Yeah, if an invasive species comes in and there's no way to get rid of them and they love eating the natural flora and fauna, guess what? You're going to have a problem. So, yep. Talk to me about the emerald ash borer. Oh, you're going to have to look that guy up. Here you go. Emerald ash borer. Ha ha. Yeah, this guy right there. Tell me a little bit about him. All right. All right. Biotic factors: predation, herbivory, parasitism, mutualism, disease, and competition. Competition can be intraspecific competition. Competition between the same species. Hey, look, you're both competing for the same grade. If I'm only handing out one perfect score, guess what? There's a competition. You're all competing to be valedictorian. So, yep. Stabilizing population numbers produces S-shaped curve. So let's take a look at this. S-shaped curve. Haha. Images. Yeah, that's an S-shaped curve right there. So, yeah. And we're right here. Good. Population small equals small amount of competition. So, look, if you got a small class, like if you're trying to make the basketball team and there's only 100 students and per grade, so for high school it's 400 students. 50 of them will be with your gender for the basketball team you're trying out. So now you're down to 200. It's a lot easier to make that team than it is a team at a larger high school. So because smaller competition, population will grow. You will flourish. As the population grows, so does competition. Let's bring that to right there. Eventually, carrying capacity is reached. And remember, what carrying capacity is the amount of individuals an environment can hold and sustain. And ecosystems can't support any more of the species. Once you reach carrying capacity, people start dying. Stronger or smarter individuals then consume more. So it's the way it is. It's not the strongest that survive, it's the most adaptable. Many become territorial, fight off competitors. The biggest territory is held by the most successful at reproducing. So yeah, it's probably the best at living. They get to live longer, survive longer, and reproduce. Interspecific competition is competition between different species. So what you have out there is the coyotes are competing against the foxes. Competition for the same resources. They're both competing for those yummy squirrels. Sometimes both species share the resource. Other times, one species outcompetes the other and one of the species has to leave or die. Competition reduces carrying capacity. No bones about it. So if you have competition, there's only so many of you that the biome can hold. Competition reduces that, where if there is no predators or regulation on your numbers, the carrying capacity is going to go up. What is the limiting factor to plants in our New England forest? Ooh. Excellent question. Hint: It's why forest flowers bloom in springtime and not during the summer. Ooh, okay. Yep. Define these terms. Page 110, or you can Google them. Predator, prey, carnivores. Good. All right, we're going to scoot that down some to right about there. Good. Types of interaction. Predation. Predator kills and eats prey. Yep, that's what predators do. Predators are carnivores. They eat meat. So negative feedback controls the population. So if you're a lion, you're not going to go out there and just... Actually, let's break it down for our community here in New England. If you are a coyote, you are not going to go out there and kill all the ducks and eat all of them in one shot, because then next week you're going to be starving. So you're going to go get one whenever you're hungry, and you're not going to overkill. So that's what a negative feedback control, how it controls the population, just with coyotes and the ducks in that situation. Herbivory is animals eating a green plant. It's that simple. Some plants have defense like thorns, toxic substances. Most of them don't. Herbivores can be big or small. So the idea that you can't be big by being vegetarian is false. Look at an elephant. They are huge and they only eat vegetables. Granted, they do spend all day eating, but they are huge and only eat vegetables. Parasitism equals one species lives in or on another. So parasite gets its food from the host, but doesn't try to kill the host. High parasite populations cause host death. Think of this with, actually that's going to give it away. Talk to me about Mus dermacetor albitapictus. All right. Yeah, just in case you're wondering if you can pronounce these, I have difficulty too. Just keep rolling with it. Mutualism is a relationship between two species and both benefit. Lichen is an example. Lichen have fungus underneath and green algae on top. The algae does the photosynthesis, so they do like getting the energy, and they make the sugars, and the fungus takes these sugars underneath. So it sounds like one-sided, right? Like, okay, the algae makes the sugars and then the fungus takes it. But the algae takes minerals and water from the fungus. So they both get something out of this. Example is leguminous plants and rhizobium, nitrogen-fixing bacteria. So the nitrogen-fixing bacteria basically soaks up all the nitrogen in the soil. It's rather cool. And then basically passes it along for the plants to use. Beans are an example of this. Planting beans is great for soil. Give 3 leguminous plants. Oh man, I gave you one already. Last paragraph, page 111, or look up online. So, yep. Rhizobium live in root nodules of the legumes. Absorb nitrogen from the soil, give it to the legumes. Legumes give ribosomal sugars from photosynthesis. So as the nitrogen gets absorbed by this bacteria and then it passes it on to the plant then gives sugars back to the bacteria. So legumes can live in crappy dry soil because of this. Yeah. Plant beans where you got really lousy soil, because they will do fine. In fact, they'll actually enrich the soil. Define these vocab words, page 110, or Google them. Saprotrophs, scavengers, detrivores. Yep, want to know what those are. Saprotrophism, organism that feeds on dead matter, important because it recycles the nutrients. How are vultures and the bacteria in compost bins alike? Probably both have to do with saprotrophism. Scavengers feed on decaying flesh. Detrivores and decomposers. Detrivores take in dead organic matter, then use enzymes to break it down. Earthworms, oh, that's another one that's usually in the compost. Crabs, millipedes. Yep, they just love dead stuff. Lobster too, I think, for that one. Yeah, actually lobsters do that. They're kind of like the cockroaches of the seas, but they're expensive. Decomposers secrete enzymes to break down the dead organic matter, then absorb it. Think of bacteria. Spiders are also kind of like this. A lot of them, they'll like secrete an enzyme. It goes into the insect, it breaks down the inside, turns their insides into like jelly, and then the spider comes along and sucks it right out. Diseases. Pathogens are organisms that cause harm to its host. You have bacteria, protists, viruses, fungi. Yep. Think of viruses. Think of what we just went through with COVID a few years ago. So, yep, that's a pathogen for you. The more dense the species, the easier it is to spread, which is why we quarantine and spread people on out during COVID. Examples are the potato blight, ergot, rabies, tuberculosis, and COVID. So, yep. Define these vocab words, page 113, or Google them. Limiting factors, carrying capacity. Hey, look, limiting factors and carrying capacities, you're going to use a ton in IB, specifically with this course in ESS. You can put that down for probably conservatively half the questions. Yeah, and work that in. Dead serious. They love them some carrying capacity and some limiting factors. Limits to population size. Limiting factors restrict the population growth. Yeah. So carrying capacity is the population limit. So what is the carrying capacity of your school? What are the limiting factors? Ooh, okay. So yeah. How many students can our school have? Why can we only have that many? All right. Biotic limiting factors. Predation. Yeah. Who's getting preyed on? Lack of food. Because without food, that really limits the amount of people you can have, or animals. Herbivory, that again is back to food and predation. Lack of a mate. Yep. Because if you could be living your best life, and without a mate, you will die and not reproduce, and genes no longer go anywhere. So, yep. Interspecific competition. That's competition in between different animals. And interspecific competition, the competition between your own same type of animal. So, yep. Abiotic factors, the ones that aren't living, are going to have oxygen, light, water, temperature. Why? Because if you take away light, everyone's going to die. They don't have enough vitamin D. Hope for no volcano explosion where it just covers the world in ash. We'll get dinosaured. Oxygen, needed to breathe. Without it, nope. That's a definite limiting factor. Just to ask if you try to go on the moon without oxygen. All right. Or actually climbing mountains can do that too for you, for Everest. Water. How long can you go without water? Not long. Temperature as well. You have a certain temperature range that you do well in, if you overheat in that, you don't do so well in, and if you go below it, it's hypothermia and you die. So yep. Define these vocab words, page 114, or Google. Density dependent limiting factor and density independent limiting factor. Yep. Density dependent limiting factors mostly decrease the population growth at population increases. So mostly population decreases the population growth at the population increases. So this is a negative feedback. What this means is like getting back to this S-shaped curve. As it starts to go up right here, that's where it starts to level out. So, where was I? Negative feedback for it. So, predation. The prey as the population increases, attracts more predators. So, that's right. This is actually happening out in Cape Cod with this animal. Cape Cod seals. Yeah. Cute, right? Look at them. There's tons of them, right? And because there are tons of seals, there are tons of these. Yep. Yep. Oh, yeah, right there. Yep. White shark on Cape Cod. Tossing up a seal. Yep. That's what they call Uber Eats. As long as that shark's name is Uber, It's going to eat. All right, so then you have the prey population decreases. So if the seals go away, guess what? The great white sharks are going to go away. They're only as faithful as their options. And if their options are starving or going somewhere else for food, they're going somewhere else for food. So, yep. Competition within the species. Population becomes dense. Competition increases for limited resources. So, unfortunately, with human growth, our population is continuing to grow. So there is more competition for those resources. Look right now at the price of oil. There's a very limited amount of oil out there. And because we have more humans on this world, we are competing more with other humans for that oil. So that the price of it goes up. Light, water, mates, shelter, food, etc., oil, that sort of stuff. Diseases and parasites. Diseases increase with population density. So the more humans you have in an area, say in a classroom, the more likely that disease is to spread around. Now, the more spread out you are, the less you have in a classroom, the less likely that disease is to spread. So parasites, the same as diseases. The more concentrated you are, the more they're going to spread. Waste accumulation. This is another one. High population density equals more waste. The more humans you have, the more poop there is. So, yep. Can kill or impair reproduction. So, yep. If there's enough if there's enough waste around, that's going to increase your diseases, and then it's going to kill off some, individuals in society. Density independent limiting factors affect a population the same way regardless of the population size. It doesn't matter if it's 5 individuals or if it's 5 million individuals. Wildfires, there's one for you. Extreme temperature would be another. As extreme temperature affects you whether you are 5 people or 5 million. Population does fluctuate over time. Nothing stays static. Nothing stays the same. Population tends to cycle. Cyclical oscillations, repeating rises and drops in the population size over time. A graph of this looks like waves. So let's go through this. Oscillate. Yeah, just like that. All right. So population goes up, then it goes down, then it goes up, then it goes down. Very good. So usually occurs because of interactions between at least 2 species. So there's usually more than 2, but it's always at least 2. Why you have something go up, every action there's an equal opposite reaction. So population growth, J curves, lack or minimal limiting factor. So yep, there you go right here. So what happens is exponential growth. It just goes boing and goes through the roof. Usually it's what they call a boom or bust pattern, because once it gets to a certain point, it's like ecosystem can't take it anymore, man. And it just collapses and goes. And as it collapses, the whole population just crashes. This is common with small mammals, fish, and invertebrates, not with humans. So if that happens, it's because there's a lot of things we did wrong. So I would love it if you could draw this graph. Use the term dieback and overshoot in a sentence in relationship to a J-curve graph. Yeah, right? Yeah. Yep. Want you to do that. Woohoo. I'll put this right here just so you don't get lost with it. Good. Yeah, let's do this. Good. All right, S curves has limiting factors. Population growth slows until the carrying capacity is met. And it's more gradual too. Environmental resistance is part of the graph after the exponential growth. So it's that part up top right here. That's the environmental resistance part. So it's after you've had your startup and then you're like, boom, your big boom period where you got exponential growth, and that's where you start to level off up there. That's the environmental resistance. Population fluctuation usually happens because carrying capacity changes for the better or worse. So, in my experience, usually for the worst. Human carrying capacity. All right, maybe that's making me a liar. There's things we do that increase carrying capacity, like importing food to an area. Human ecological niche. Through technology, we have expanded our niche. We're able to live in different climates. Let's bring this down here. Oh yeah, you gotta draw this graph too. All right. Through technology, we've experienced our niche. So, expanded our niche. Able to live in different climates. Difficulty in measuring human carrying capacity, though, for a few reasons. We use a greater range of resources. So, like, we adapt better than any other animal out there. So if the potato blight happens, guess what? Maybe we switch to sweet potato fries. I'm sure we'll cry over it, but we'll live. We'll do fine. So we switch resources for other ones as needed. Interspecies resources use varieties a lot. So predators have been minimized. Yeah, if you noticed, there really aren't too many vicious black bears in New England. Why? Because all the aggressive black bears in New England were hunted out over 150 to 200 years ago. The only ones left are the ones that are basically, you know what, we lost this, we're not fighting the humans. So they don't take us on, unless it's a mama bear with cubs. And she's cornered. So, yep. Consume immediately at the expense of long term. Sounds like us, right? Yep. Why worry about 50 years down the road when we got a problem right now? So we don't really have a long-term outlook for humanity as what we should. We import resources as well, which expands our carrying capacity. So what would the carrying capacity of Hartford be? Hartford, Connecticut. Not all that great. There's not a lot of land to farm, so getting food would be rather tough. The Connecticut River, I don't know the shape of it. I don't think you're getting too many fish out of there. So fishing is not an option. So what Hartford does is we import food, and that increases the carrying capacity of that ecosystem. Technology, fertilizers increase crop yields. So, you start looking around the cornfields around our school where, what we've grown. And what we do is we put fertilizer into the soil every year to help that crop grow to its fullest so we can make the most money and most crop, basically, out of that acre. So fossil fuels increase shipping so we can send food all over. That by the time you're eating a strawberry from the supermarket, it's flown in from California probably. It's more than halfway across the country. So medical technology increases life expectancy too. We have the ability to keep people alive a lot longer. As they're alive a lot longer, they consume quite a bit more resources. It's just the price of doing business. So the problem is overusing farmland right now. We do a lot of monocultures, it's just one type of crop. The problem is that we're betting on that one crop always being there, giving us like that high paycheck every year. And the problem is if it doesn't, then that farm goes broke or bust. Granted, there's insurance on it, but it doesn't do us really any good. Really, what you want to do is more diversified crop farming. So, ways to change human carrying capacity, ecocentrics. This is an ecocentric viewpoint to it. So, ecocentrics minimize renewable resources. Just play around with that for a second. We reduce non-renewable resources and go off-grid or homesteading. Yep. It's basically where you're just like, I don't need anybody to survive. I've got my house. I produce all my own food. I produce all my own energy. Leave me alone. Get off my land. Get off my yard, kid. So, yep, that's those people. There are people like that. They can do that too. They're not overly making fun of them as much. But technocentrics say carrying capacity can be expanded, right? So that means they can put. Their thinking is they can. This world can have even more people. So Elon Musk is one of these people that thinks this way, and history can back him up a little bit, actually. History examples: fertilizers have increased food production, so that's what allowed us to have more people. Refrigeration keeps food longer, keeps it from spoiling. We have less waste. Medicine keeps people alive longer. So all three of those right there have increased the carrying capacity currently compared to 300 years ago when we didn't have any of those. So ecological versus conventional economist. Conventional say trade increases carrying capacity because you're importing goods and you're trading resources, one that you're rich in for one that you're poor in. Economists say the opposite. Tech increases speed we use resources. So you just go through stuff faster. So increases carrying capacity, but now expensive long term. So they kind of want to shift us to is reuse, recycling, remanufacturing, and absolute reductions. So reduce environmental demands to increase carrying capacity. So reuse objects used more than once. Think of pre-owned cars. Some of you already do these, by the way. So don't think it's like too cray-cray. Reuse soda bottles after being washed. I talked about it last chapter. In Germany, that's what people do with beer bottles. They basically will buy a bottle of beer, they will consume the liquid, and then they will bring it back to the store. They'll get washed out. They'll put more beer in there, and then someone else will buy it and then drink it. So, yep, and that bottle has multiple lives without being reformed or changed. We recycle objects. The material is used again to make a new product. Aluminum cans being melted and reformed takes little energy and can be done for virtually forever. Huge supporter of this is Jason Momoa, who is Aquaman. He had his own he's got aluminum water bottles, so that you just buy water and you drink it, and the aluminum gets recycled. You no more plastic waste all over the place. Plastic bags recycled into fence posts. That's another one. I haven't heard about plastic bags being recycled into fence posts, but I have heard about tires that go into decking material and other things. Remanufacture objects material broken down to remake the same object. Water bottles, some clothing is like this. My clothing brand that I really like is Patagonia. They will take a lot of your material that's like synthetic, that's got like stretch to it, and elastic, which it's because it's got plastic in it. They will take it and then remanufacture it to work it into new material, so that they're not having to buy new like plasticky synthetic material. They're just reusing the stuff that you have. Oh yeah, don't get me wrong, you bring it back to them and they'll probably give you a discount. They'll buy it back from you. So absolute reduction, using fewer resources. Not as useful because as the population increases, the amount of resources used increases again. So using fewer resources, but then that just makes the population grow, and as the population grows, the total amount of resources gets used. Less example is less packaging on a product. So yeah. All right. Limits to human carrying capacity. Let's bring that one actually. Yeah, right there. The year was 1798, just after the American Revolution. We were trying to expand, I believe, the Northwest Territories, but before the War of 1812. So the population was 1 billion in the whole world. Yeah, in 1798. The economist at the time named Thomas Malthus, and I'm not sure if I pronounced it right, but we'll roll with it. The power of the population is infinitely greater than the power of the earth to produce subsistence for man. Which means population's at 1 million. You're not getting any further. Earth can't give you any more. In the year 1976, which is roughly not quite 200 years later, The population was 3.5 billion. Kind of made Malthus look like a liar. So, environmentalist Paul Ehrlich said, famines of unbelievable proportions, that's what he was predicting, feeding 6 billion peeps would be totally impossible impractical. The only problem is in 1999 we surpassed 6 billion people. So yeah, it's like every year there's a new benchmark, a new being settled, and we are still living. So that's the thing with it that really backs up those technocentrics, because like they're like, yeah, look 300 years ago what the population, what the carrying capacity was, and I passed it using technology. So yeah, there's some truth to it. Ecosystem stability. Open systems equal sustainable systems. So tropical rainforests are an example of that. They are less than 2% of the land, but 50% of your biodiversity globally resides in that 2% of the land. It's got high inputs plus outputs plus storages. It'll store a ton of carbon. 25% of all land-based carbon is stored in your 2% rainforest. So deforestation of rainforest is extremely bad. It comes at the expense of logging, burning, conversion to agricultural results in the trashing of the rainforest. And it happens quite a bit down in Brazil because, they're burning the rainforest to make soybean farms. Talk about that maybe later in a bit. Less habitat equals less biodiversity. Yep. Can't have as many animals if you've got less land. Break it down into that simple. Thing is too, it's not reversible. It's not as if like you can burn down a forest and be like, okay, farming for a few years, okay, yeah, we're gonna move on to something else. Maybe be an Uber driver, maybe work for Amazon, and then the forest will grow back. Yeah, it'll grow back, but it takes like hundreds of years, and really that's not sustainable, and it's really not even like some of those trees are over 500 years old. It's really irreversible. So, keystone species will also play a most important role in maintaining ecosystems. Examples for keystone species are sea otters, beavers, elephants, wildebeest. You learned about wildebeest pretty much last year in bio with the savannah. Think about your quarter one bio in 10th grade. So, define biosphere, page 121 if you'd like, or any other source that you'd choose to use. Biosphere integrity threshold. So the book shows a model that shows biosphere integrity surpassing a critical point because of habitat loss. Extinction rates increase indicates the truth to this. So, so basically, with habitat loss, you're going to have, it reaches a critical point where that species is no longer survivable or sustainable, and it crashes and you don't have it anymore. So what is a clade? A clade is a taxonomic group which contains one ancestor and all of its descendants. Cladogram is another word for is a phylogenetic tree, is an evolutionary tree showing ancestral relationships of organisms. Back in the day, it's how animals presented. So you were like, oh, wow. That's an animal that was walking on its hind legs. Cool. Oh, it's got two other arms. Oh, cool. We'll call it a human. All right, it's got some hair. Oh, that's pretty cool. Hey, there's another animal walking on its hind legs. It's got hair too. Wait a minute. It's a bear. Oh, bears and humans must be related. No. Okay. But that is how back in the day how they used to do it. It was just how they presented. The problem is different animals can evolve separately but have the same physical characteristics. So, yep, just the way it is. All right, nowadays DNAs, you have to do it, your DNA has to be similar. Yeah, we've progressed a little bit. Got smarter. So, oldest ancestor is nearest the trunk, and the newest ones are further away. It shows the evolution of a species. So, yep, pretty good for it too, just to see how it evolves, and just like a tree, it branches off. A niche is where an organism best fits into an ecosystem. There's two types of niches. There's fundamental niche, the full range of conditions for a species to survive and reproduce. This tends to be a larger, so more like think of fundamental niche as like the textbook definition of like, okay, this is what it needs to have. And then there's the realized niche, which is the actual conditions species exist in. Tends to be a little bit smaller niche. So you're like, yeah, humans. Oh, you can survive in the Arctic. Not many of us really could. So K and R strategies, reproductive strategies, otherwise known as K and R selected species, in case you find it in a book somewhere else. So if you find it in K and R and they're talking about strategists or reproductive strategies or selected species, it's the same thing. K equals the carrying capacity. So that's what an environment can sustain without overdrawing its resources and the species dying. R is the shape of the exponential growth curve. So, yep, let's see if we can get that. See if we can get an S wave up again here. S-shaped curve. Yeah, images. Yeah. So right about here, that's your R strategist. So, yep. Back to this though for a second. All about passing on genes to the next generation, whether you're a K or R. It's basically it. Most species show a mix of both strategies. So there's not one that really fits. There's very few of them anyway that fit purely just one. Most of them are somewhere in between and take a little bit of both. So there's a bunch of these that you could identify with. K strategists tend to have long lives, reproduce slowly. Most offspring live. Think of elephants, humans too, actually, to be fair. Our strategists tend to be short-lived, all right, but they grow and mature really fast. More offspring die. A lot of fish are like this. Insects are like this. Cats tend to go more along those lines too. There's other changes for both of them. Name a K strategist and R strategist from the ocean. Oh yeah, you're gonna have to look that one up, I think. Can't use swordfish or sardines, which is in the next part. Swordfish are K strategists and sardines are R strategists. Which of these is more sustainable to fish for and why? Sardines! Alright. Mostly because if you're listening to me, great. Sardines, you could fish for them, take them out of the ocean, eat them. Yummy, right? They're reproduce. They're gone, and they're literally nature makes more of them tomorrow. So that's why. Where swordfish, they take years to produce. So when you take a swordfish out of its environment, it's not getting replaced for years. So, yep. Ending with some good news. Pandas are K strategists. They've been upgraded from the endangered to vulnerable on the IUCN Red List. Yeah! All right, so they're no longer on like the super endangered list. They're just vulnerable now. All right. The reason is less fragmentation of land. So what they did is they're like, with land being fragmented, it's like, okay, we have a spot for pandas here, and then we have another spot for pandas here. Well, how the heck are those pandas ever going to meet? What they did was they basically took the land in between. They're like, and they made a little corridor for it. So now, like, this panda here can live here, but when it wants to reproduce, it just goes up the corridor to visit the other panda, and they make panda babies. So, yep. If you want to know about that, reference your health class. So, yep. Let's do this. Let's minimize my face here. And then, yeah, just like that. We'll see if this works here. Right there. Oh, I got a couple of questions right here. Let's see what we get here. All right, so it looks like you got 4 types of evergreens here. Some of the trees found in the forest of California. Oh, cool. Oh, they're evergreens too. All right. They're not losing their needles anytime soon, I don't think. All right. Are the leaves needly spikes? Okay. Yes is species A. All right. So probably the needly spikes are this one here, Sitka spruce. Oh, yes, A. Sweet. No, go to question 2. All right. So are the leaves needles scaly? That one looks scaly there, the giant sequoia. Yeah, I got it right. Awesome. Okay, no, go to question 3. So far we've done the Sitka spruce and the giant sequoia. All right, so are there small seed cones at the end of the stem? Oh, yeah, there are right here. Coast redwood. Awesome. Oh, so species B is probably the one that's left over, the western hemlock. Hemlock, the wood for hemlock is really good for building. It's, I forget if it's insect repellent. Let's see. This is the sort of stuff I like. Why is hemlock wood good for building? All right. Let's go for all. Okay, smooth grain but durable. It's resistant to wear and tear, which makes it ideal for parts of buildings that experience a lot of traffic. Oh, okay. This is for structures, especially in the farm. Yeah, cool. Yeah, so if you got like steps made out of hemlock, you're probably doing pretty well. That see a lot of traffic. All right, let's get this good. All right, moving on down. So, giant sequoia, Sequoiadron giganteum, cones containing seeds right here. Longhorn beetle. Oh, why do I think that's going to be in a species that's going to cause damage? With reference to figures 4b and 4c. Oh, that's these two right here. State the species interaction between the giant sequoia and the longhorned beetle. All right, so, all right, that's going to be some sort of parasite, mutualism, something like that. Oh, state one value of the giant sequoia. So you're probably going to have to do a fact file down here on the giant sequoia. They are legally protected in California. All right. They're adapted to periodic fire. Historically, wildfires have occurred in California every 6 to 35 years. They have thick bark. Yep, the heat fire dries the cones. Oh, they're adapted to periodic fire. That's actually good. Yeah, seeds can be also released by the longhorned beetle. Oh my god, so that might be mutualism right there. They eat the cone, releasing the seeds. Yeah! All right, look at that right there. Mutualism. Yeah, sweet. All right. That's with reference to figures 4A, 4D. Identify one reason why the giant sequoia is listed as endangered in the International Union of Conservation of Nature, IUCN Red List of Threatened Species. Ooh, okay. Yeah, looking at that, all the yellow and looking at the green, probably got to find a reason why it's endangered. So, all right, peeps. Hopefully you're doing awesome. Keep rocking. I know this is a long and a fast one, so, yep, we'll get there.